In the first 3 sections of Chapter 2, we talked about a variety of different counting techniques. That is, different ways of trying to enumerate or count how many ways there are for a particular outcome to happen. For the next 2 sections, we're going to talk about how to apply those counting techniques to help us determine probability. So probability is a term that's used to describe experiments in which the outcome is subject to chance in some way and cannot be predicted with any certainty. We're going to look at discrete probability, which is the likelihood of an event happening when the possible number of outcomes are distinct events. So let's start with the definition. Suppose an event E is a subset of some finite sample space S. So E is just a collection of certain events from some finite space of events S, of equally likely events. So think, the different outcomes of rolling a die or flipping a coin. The probability of an event E occurring is given by the following formula. We write P of E to mean the probability that event E occurs, and it's given by the formula the cardinality of E over the cardinality of S. Remember what these absolute value bars mean when we're talking about sets? It just means how many elements are in this set. So essentially what this number is the number of desirable outcomes divided by the total number of outcomes. Okay, and notice that since E is a subset of S, this means that the cardinality of E is definitely going to be less than or equal to the cardinality of S. And we know that for finite sets, that the cardinality is guaranteed to be greater than or equal to 0. So essentially what this tells us is that the probability of event E occurring is always going to be some sort of a fraction where the numerator is less than or equal to the denominator, which means probability is always going to be a number between 0 and 1, including possibly 0 or possibly 1. But it's some real number between 0 and 1. And we often rewrite it as a percentage. So for example, if the probability of some event occurring is, let's say 1 over 2, let's say the probability of flipping a heads when you flip a coin is 1 over 2, that's like 0.5 as a decimal, but we could write that as a percentage by moving the decimal point over 2 spaces to the right, giving us 50%. All right, but that probability, it has to be between 0 and 1, meaning that percentage has to be between 0% and 100%. If you're ever computing a probability and you get some fraction where the numerator is bigger than the denominator, you messed up. Go back, see what you did wrong, because probability always is between 0 and 1, or 0% and 100%. So let's look at a few examples. So suppose you roll a normal 6-sided die. Find the probability of rolling a number greater than 2. All right, so let's think about what our sample space is here. Those are all of your possible outcomes. Well, it's a normal 6-sided die, so the sample space is just going to be all the different outcomes you could have, namely rolling a 1, a 2, a 3, a 4, a 5, or a 6. In this case, we're trying to find the probability of rolling a number greater than 2. So our event that we're looking for here is rolling a number greater than 2. And that's going to be, well, all of the numbers from this set that are greater than 2, namely 3, 4, 5, and 6. And so the probability of rolling a number greater than 2 is going to be cardinality of E over cardinality of S. Well, there's 1, 2, 3, 4 elements in E, and there are 6 total elements in S. That is, there's 4 favorable outcomes. There's 4 outcomes that are numbers bigger than 2, and 6 total outcomes. We can reduce this to a probability of 2 over 3, or if you wanted to, you could rewrite this as about 66.7%. That's rounded off, so I'll just do squiggly equal signs for rounding. All right, let's look at another example. A normal coin is flipped 10 times in a row. Find the probability that exactly 3 heads appear. Okay, so it's helpful to think back to one of the warm-up problems that we did, where we counted the total number of outcomes when you flip a coin a bunch of times in a row. All right, so if we think about the sample size here, it would be difficult to list out all the possible outcomes, because an outcome here is just going to be what happens when you flip a coin 10 times in a row. Well, you could get all tails, you could get 10 tails in a row, you could get 10 heads in a row. Oops. You could get some combination of tails and heads, tails, 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 heads. Okay, well, obviously it's not going to make sense to list out all the different ways. So in this case, it's easier to just find the cardinality of the sample size. That is, count out all the different number of ways that you could flip a coin 10 times in a row. For this, we use the multiplication principle. Right, there's 10 outcomes that are happening here. Each time you flip the coin, you're either going to get a heads or a tails, so there's 2 outcomes every time. And so the total number of outcomes is 2 to the 10. Right, so our sample size, our sample space has a size 2 to the 10. All right, now we want to find the probability that when we flipped that coin 10 times, we got exactly 3 heads, which means our E here is going to be all of the different sequences of 10 heads or 10 coin flips where you have exactly 3 heads, and thus you would have exactly 7 tails. Again, I don't really want to list out all the different possibilities. You could have heads, 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 and then the rest tails, or they could be mixed up in any number of ways, right? A whole bunch of different ways. Maybe they come at the end, maybe they're all mixed up. But I don't really want to list all the different ways. Whoops. This is going to keep going. So instead what I'm going to do is I'm going to find the cardinality of this set using the counting principles that we learned in the last section. Right? So we're trying to figure out how many sequences of 10 coin flips result in exactly 3 heads and exactly 7 tails. Well, there's 10 spots here, and we want exactly 3 of them to have a heads. Right? Once you've chosen 3 of those spots to be heads, let's say you chose this one, and this one, in this set of allowable outcomes and our desirable outcomes, the rest would have to be tails. So we simply need to count how many of these outcomes have exactly 3 heads. Well, how many ways can you choose 3 spots out of 10 to have a heads in it? That's just going to be 10 choose 3. Right, there's 10 spots to choose from. We're going to choose 3 of them to be heads. Remember, this number is the same as 10 factorial over 7 factorial times 3 factorial. What's that equal to? If you actually do this computation out, you get 240. And so finally, we can find the probability that we get exactly 3 heads by dividing the cardinality of E over the cardinality of S. That is the favorable outcomes, 240, divided by the total number of outcomes. That's 2 to the 10. All right, maybe you can reduce that, maybe not. I don't particularly care. You don't really need to reduce it unless they ask you to. All right, let's do one more example. You pull a card from a normal deck of cards, okay? What's the probability that you pulled either a heart or a king? Let's think about our sample size here, or sample space. This is just going to be the set of all cards in the deck. And so the cardinality of this set is just how many cards are there in the deck. There's 52. All right, now our favorable outcomes here, the outcomes that we're looking for, is any outcome that results in either a heart or a king. All right, so let's think about what you could get here. Well, ace of hearts would work, the 2 of hearts would work, the 3 of hearts would work. Any one of your hearts would be a good allowable outcome here. So all the way up to the king of hearts. Okay, so there's 13 heart cards. And then another allowable outcome would be a king. Well, we've already accounted for one of those kings, but there's 3 other outcomes that we want to count here as possible good outcomes, the outcomes that we want. That would be king of diamonds, king of spades, and king of clubs. Okay. And so the cardinality of this is just the number of cards that are either hearts or kings. All right, so this first group here, the number of hearts is 13, and then we get an additional 3 kings. We don't want to double count this one in the middle. And so in total, the allowable outcomes here, or the desirable outcomes, would be 13 plus 3, which is 16. And so the probability of pulling a heart or a king is going to be the cardinality of E over the cardinality of S, that is 16 over 52. Okay. Now sometimes it can be tricky when you're trying to calculate a probability and the event that you're looking for contains an OR statement. Right? So I was able to directly list out all the different cards that were either a heart or a king. But in some cases, it's not really going to make sense to list them all because there's going to be too many. And so we can use the principle of inclusion-exclusion to help us find the cardinality of this particular set. Remember what the principle of inclusion-exclusion said. It said, I'm running out of space here, but let me add a note at the bottom. Principle of inclusion-exclusion would tell us that if we wanted to count the number of cards that were either kings or hearts, so that union symbol means or, we could count the number of kings, then we could count the number of hearts, and then we could subtract the cards that were both kings and hearts, right? Because we double counted the ones that fell into both of these sets, so to account for that double counting, we subtract. The principle of inclusion-exclusion is going to lead us to a way of finding the probability that one event happens or another event happens. Let's look at an example of that. Okay, well, we call this the addition rule for probability. So given 2 possible outcomes, A and B, that are both contained in some sample set S, the probability that A or B occurs is going to be given by the formula, the probability of A plus the probability of B minus the probability of A and B occurring. All right, so just to make sure we understand what this is saying, let's go back to that last example and try and use this addition rule for probability and make sure that we got the same probability in the end. All right, so we want to find the probability of drawing a king or a heart. All right, well, according to this addition rule for probability, this should be equal to the probability of drawing a king plus the probability of drawing a heart minus the probability that you drew both, that you drew a king and a heart. All right, so let's go through and see what we get here. The probability of drawing a king, well, there's only 4 kings in the entire deck of 52. So the probability of drawing a king would be 4 over 52. The probability of drawing a heart, well, the hearts are 1/4 of the entire deck. It's going to be useful, though, if we have the same denominator here, so I can say out of the 52 cards in the deck, 1/4 of them are hearts. That is, there's going to be 13 hearts in the deck, namely ace, 2, 3 through 10, and then jack, king, queen. Finally, what's the probability that we draw a king and a heart? Well, there's still 52 cards in the deck, but there's only one card that satisfies being both a king and a heart, and that is the king of hearts. So the probability that you pulled the king of hearts is just 1 out of 52. So adding this all together, we get 13, 14, 15, 16, 17, minus 1 is 16 out of 52. That's the same thing we got in the last one. So we see exactly how this works here. It's really just using the principle of inclusion-exclusion. Because the principle of inclusion-exclusion would have given us, okay, there's 4 kings, there's 13 hearts, but we subtract how many are both kings and hearts. So this rule here is just an extension of the principle of inclusion-exclusion for probability. Okay, let's do another example. A family has 5 children. If having a boy or a girl is equally likely, what's the probability that the family has all girls? Okay, so this isn't necessarily going to be an addition rule here. This might just be another probability problem. So let's think about what our sample space is here, and let's think about our outcomes. Okay, so our sample space is just the number of possibilities you could have if you have 5 children and each child is a boy or a girl. All right, so just like before, we could list out all the different possibilities: boy, 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 girl, boy, girl, boy, 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 right? We don't actually want to list them all. So it makes more sense to just find the cardinality of the sample set. All right, well, they have an oldest child, they have a second oldest child, a third oldest child, a fourth oldest child, and then a youngest child. Each one of these children can be either a boy or a girl. They're telling us that it's equally likely. And so there's 2 options for each child out of the 5 children. And so there's 2 to the 5th power, or 32 different possible outcomes here. All right, now how many of those outcomes consist of all girls? Well, you had to have a girl in the first case, you had to have a girl in the second case, you had to have a girl every single time in order to be one of these allowable outcomes here. So there's really only one option for the first child, one for the second, one for the third, one for the fourth. There's only one option here. So only one possible option here is an allowable outcome. And so the probability of having all 5 girls would be 1 over 2 to the 5th power, or 1 in 32 chance. All right, what's the probability that the family has at least one boy? All right, well, the sample size is still going to be 32, just like before. There's 32 possible outcomes because each of the 5 children is going to be a boy or a girl. So what's our, what outcomes are we looking for here? So we want the different outcomes where, excuse me, out of those 5 children, at least one of them is a boy. Well, there's a lot of possibilities, because you could look at the possibilities where you have exactly one boy, so all the different ways that you could have a boy and 4 girls. Or you could have, let's see, 1 boy and 4 girls. Or start with a girl, then a boy, then 3 more girls. Or girl, girl, boy, girl, girl. Okay, I'm already starting to get tired of this. And that's only listing out the different possibilities if you have 1 boy. Then you need to consider having 2 boys. You could have boy, boy, girl, girl, girl. Or you could have boy, girl, boy, girl, girl. Yikes, I don't really want to keep listing them all. You could have 3 boys, you could have 4 boys, you could have all 5 boys. So it gets a little bit tedious to list them all, right? Except here's one thing to notice. In the last example, we said that there's only one possibility in which all of the children are girls, right? That's if you have a girl every single time. If this isn't the case, if your family did not have all girls, that means that they must have had at least 1 boy. So there's only one case, or there's only one outcome in which the family does not have all girls. Does not have at least 1 boy. That is, namely, the case where it has all girls. And so if there are 32 outcomes, then that means in every single outcome except the one we saw in 4A, they're going to have at least 1 boy. So 31 outcomes contain or have at least 1 boy. And so the probability that the family has at least 1 boy is equal to 31 over 32. What we're using here is the fact that in all of these possible outcomes, in all of these 32 outcomes, we know that they're either going to have all girls or at least 1 boy. In other words, the event of having at least 1 boy, in some sense, is the complement of the event of having all girls. And we saw in the counting chapters, or actually maybe even in the set cardinality chapters, that the cardinality of some set A is equal to the cardinality of the entire universe minus the cardinality of A complement. We're using this idea right here to give us a theorem about the probability of the complement of an event. Okay, so if E is some event in a sample space S, and E bar represents the event that E does not occur, then the probability that E does not occur should be equal to 1 minus the probability that E does occur. Why is that? Well, within this universe, either E occurs or it does not occur, right? One of those two things has to be true. So we have that the probability that E occurs plus the probability that E does not occur has to be equal to 100%, or written as a decimal, just the whole number 1. Rewriting that gives us this rule here. And you'll find that it's often easier to compute a probability by finding the probability of the complement and then subtracting from 1. So we'll do just one more example here. If you roll a normal die 10 times in a row, what's the probability that you roll a 6 exactly once? All right, so our total outcomes here, well, let's see what we're doing. We're rolling a normal die 10 times in a row. So there's 10 spots. And it's a normal die, so each time you roll it, there's 6 outcomes. Right? You either roll a 1, a 2, or all the way up to 6. So there's 6 outcomes on the first roll, 6 outcomes on the second roll, all the way down to the last one, so there's 6 to the 10 outcomes. That's going to be the cardinality of your sample space. We want to find the probability that you rolled a 6 exactly once. So how many events are allowable here? Well, we're looking for the sequence of events here where you rolled a 6 exactly once and everywhere else you rolled, well, not a 6. Okay, so we need to count how many of those rolls have exactly 1 6. Okay, so let's think about what that would be. Well, the first thing we need to do is we need to choose one spot to contain rolling a 6, right? Choose one of those spots, right, in either the first roll, the second roll, or the 10th roll, all the way to the end, where you rolled a 6. How many ways could you do that? Well, 10 choose 1 ways, right? There's 10 choose 1 ways to do this. All right, having chosen that designated spot, suppose we, have to have a 6 here. Every other spot has to not have a 6, which means in every other spot, you can have a 1, a 2, a 3, a 4, or a 5. As long as you don't have a 6, it's okay. So there's 5 options here, 5 options here, right? You can have 1, 2, 3, 4, 5 here, 5 here, all the way down the line. And this spot here is guaranteed to be a 6, so there's really just one outcome for that spot. So the total number of ways that you can choose a spot to contain a 6, and then fill the remaining spots with something that's not a 6, would be, all right, we have 9 factors of 5, or 5 to the 9th power, times 10 choose 1. 10 choose 1 is just 10. So this is 5 to the 9th power times 10. Oof, this is looking a little bit messy, but now we have that the probability that you rolled a 6 exactly once is going to be 5 to the 9th times 10 divided by 6 to the 10. Whatever that number is, that's going to be your probability that you rolled a 6 exactly once. All right. Now as a follow-up, what's the probability that you rolled a 6 at least twice? Ooh, okay, so our event here is going to be rolling a 6 at least twice. So what that means is we're looking for all of the events where you rolled a 6 once, oh, no, sorry, not once, at least twice. So twice, or 3 times, or 4 times, or 5 times. Uh-oh, I don't really want to write this, so I'm just going to do ... Or the last possibility is that you rolled a 6 every single time, so 10 times. This is an OR statement, so we could use that addition rule if we wanted to, but it's going to be pretty messy to find this probability. So this is one of those cases where it's going to be easier to use the complement here. So the complement would be, well, what would happen if it's not the case that you rolled a 6 at least twice? So you had to roll the dice 10 times. If you didn't roll a 6 at least twice, that means you rolled a 6 less than 2 times. So we want to find the probability of rolling a 6 less than 2 times. So that means 1 time, once, or 0 times. All right. Well, we already know how many different outcomes have you rolling a 6 exactly once. That's what we did in the last example. We'd found that the events where you rolled a 6 one time was 5 to the 9th times 10. But we also want to consider all the outcomes where you rolled a 6 0 times. All right, so for 0 times, we're saying we rolled the dice 10 times, but we never got a 6, which means every single outcome was either a 1, a 2, a 3, a 4, or a 5. So there's 5 allowable outcomes in every single spot. And so there's going to be 5 to the 10 such outcomes where you did not roll a 6 at all. Okay. So the probability of E complement, that's the probability that we don't want to find, is this number here, the cardinality of E complement, that's 5 to the 9th times 10, plus 5 to the 10th, divided by the total number of outcomes, which we found in the last example was 6 to the 10. And now, using the theorem from above, I have that the probability that I do want to find is equal to 1 minus the probability that I don't want to find. All right, look up here. This is not exactly how it's written, but you could rewrite this equation to say P of E is equal to 1 minus P of E bar, or E complement. And so we get that the probability that we're looking for, the probability of rolling a 6 at least twice, is 1 minus this probability that we did not roll a 6 at least twice. So 1 minus 5 to the 9th times 10 plus 5 to the 10 divided by 6 to the 10. This is the probability we're looking for.